Welcome to 6.2 Rational Functions. Today we have rational functions are functions that show an inverse variation. So as you can see, if you have, no, they don't have to show an inverse variation. So that, I should have said might, that might show an inverse variation. And however, the variable is always on the bottom of the fraction. So for example, this function is x squared over 2x minus 2. The variable is there's a variable on the bottom. This function, x over x squared minus 9, there's a variable on the bottom. So functions that have an inverse variation and the variables is that might have an inverse variation, but if it has an inverse variation, it's definitely a rational function. So last time we talked about inverse variations because those are very fundamental to the rational functions that we're going to be exploring today. So this is an asymptote experiment. What is an asymptote? Asymptotes are horizontal or vertical line where inputs and outputs are available. They're in the domain or in the range, infinitesimally close to the line, but they never actually reach the line. So for example, let's say f of x is equal to 2 to the x power, right? So you have this function right here, right? You have this function. Now, as you can see in here, it reaches infinitesimally close. It reaches really close, but it never actually touches the 0 line. Never actually touches y equals 0. So y equals 0 is a horizontal asymptote of this function, and there's no asymptote for the vertical because it goes to infinity. But it never actually touches 0, even though it reaches infinitesimally close to 0. It reaches infinitesimally close to 0. So f of x is equal to 1 over x minus 3. So let's try some values. Right? Okay, let's try some values. So we all know if we put x as equal to 3, and we'll have 1 over 3 minus 3, and that is obviously 1 over 0, which is not defined. It's an asymptote. It's not defined. So let's do this. We're going to draw this graph right now. Let's try 2, okay? So we put 2 in here. What are we going to get? 2. Let's do like one of these, right? If we put 2 in here, we're going to get 2 minus 3 is negative 1. 1 divided by negative 1 is negative 1. So if we put 2 in here, we'll get negative 1. 2, negative 1 right here. Let's try 2.5. 2.5. 2.5 minus 3 is negative 0.5. 1 divided by negative a half is negative 2. So then we'll get negative 2. Let's say this is 3. This is 3, right? Okay, let's try 2.9. 2.9 minus 3 is negative 0.1. 1 divided by negative 0.1 is negative 10. So now we have this. So the graph kind of goes like this, right? And we could try the other way around now. So we'll do 4, 3.5, and 3.1. And if you try them in, 4 minus 3 is 1, 1 divided by 1 is 1. 0.5 minus 3 is 0.5, 1 divided by 0.5 is 2. And then this is 10. So we'll have 1, we'll have 2, and then we'll have 10. There you go. See? So you go down, you go up. So, what's the asymptote? It's 3. The asymptote is when the bottom is equal to 0. So similarly, for this one, what's the asymptote for this one? It's 2x plus 5 is equal to 0. So subtract 5, 2x is equal to negative 5, x is equal to negative 2.5. Negative 2.5. So the function will probably look something like no, not the function, not the whole function, but the points reaching that final function will probably look something like probably look something like this. See, and then that's negative 2.5. It'll probably look something like that, right? With this asymptote right there. So, knowing that, we are going to try to decipher some graphs. I think I picked a really hard one. But we have to match the rational function to the graph. So they all have x minus 1 bottoms, so all of their asymptotes are x minus 1. So it's x equals 1. X equals 1. That's all of their asymptotes are x equals 1. So yeah, they all have x equals 1. But 1 over x minus 1. So since it's 1 over x minus 1, there's no horizontal, there's nothing to worry about horizontal asymptotes. We'll worry about that later, but we can just plug in values. So for example, 2, what are we going to get for 2? We're going to get a 1. So which of these functions gives 2 as a 1? Nope, that doesn't look like 1. That's plausible. That's plausible, right? And this is negative 1. So that doesn't work either. So this one's this one, right? And then if we put 2 in here, we'll get 2 minus 1 is 1, but negative 1 divided by 1 is negative 1. So this 2 will point into the negative 1 direction. So this one belongs to this one, which leaves this one over here. Process of elimination really does help you decipher, these graphs. So the simple conjecture is the zeros of the denominator function are the vertical asymptotes of the function. So we're going to find some vertical asymptotes right now. X minus 6 is equal to 0. So x is equal to 6. That is our vertical asymptote. And 7x plus 23 is equal to 0. So 7x is equal to negative 23. So then we got x is equal to negative 23 over 7. And that is our vertical asymptote. Negative 23 over 7. So we're going to have a horizontal experiment now. Horizontal asymptote experiment. So these are the graphs right here of the corresponding equations. So we want to find the asymptote of each of the graphs. So for this one, this is 5. This right here, that's 5. This is 0. So each square is 1. So this is 1 right here, 1. Right? We have 1. And you could see that these lines are getting infinitesimally closer to 1. They are getting infinitesimally closer. They're never actually reaching 1. So 1 is our horizontal asymptote. This is y equals 1. The answer why it's y equals 1 is because all points of the line have the value of y equals 1. So our asymptote is y equals 1. Now for this one, it reaches infinitesimally close, but it's not y equals 1 this time, it's y equals 0. So it's y equals 0, not y equals 1 anymore. Okay, how about this one? We have, that's 1, and that's 0. As you can see, this function passes 1 at about 4. This function passes 1 at about 4. I'm not actually sure if it's exactly 4 or not. It is exactly 4. So this function passes 1 at 4. But where does it go to? Now, if you look really closely, you can't really make an accurate measurement of where it exactly goes to, but it looks like it goes to around 1/2, right? Because this looks really close to diverting to 1/2, and then this also looks really close to diverting to 1/2. So what's the generalization? Now, if you go back, I'll try. Let's see if you can find a pattern in these functions. I'm going to let you see if you can find a pattern in these functions, because finding patterns is super satisfying. You'll remember it forever. I'm going to see if you can find the patterns in these functions that led me to having the 1, the 0, and the 1/2. Okay, I'll give you 5 seconds. You can always pause the video. Okay, here is the pattern, right? So this first function, we have x plus 4, x minus 3. The first coefficient of each of the highest order terms, for example, this is an x, this is an x, and x. They all have coefficients of 1. You take them, you divide them. So 1 divided by 1, what's 1 divided by 1? It's 1. And that's your asymptote. It's 1. That's your asymptote. For this function, there's no x. Since there's no x, it's basically 0x. And what's 0 divided by 1? That's 0. So 0 divided by 1 is 0. How about this? This is 3x over 6x. So what's 3 divided by 6? That's 1 half. See, 1 half, 0, and 1. 1, 0, 1 half. That's the generalization. So horizontal asymptote, you take the leading coefficient of the terms, and you divide them together, and that's your horizontal asymptote. You divide the top by the bottom, just like how it works. Okay, so we have some practice problems. We only have 2 today because I'm kind of in a rush for making this asymptote for the top function. We want to find our vertical asymptote. So the vertical asymptote is really easy, just 63.65 over 3x plus 123 equals 0. So now we have 65 over 3x is equal to negative 123 multiplied by 3, negative 369. So then we have x is equal to negative 369 over 65. And that is our vertical asymptote. What's our horizontal asymptote? Well, it's y equals, and here are your leading coefficients right here, 48 and 65 over 3. So we can do 48 divided by 65 over 3, which is 48 times 3 over 65, which is equal to 144 over 65, and that's our vertical asymptote. So that's it. That's really all you have to do. All you have to know for this lesson. But we're gonna do a little bit more. We're gonna have another section. So there's gonna be 6.2, just kind of 6.2a, and we're gonna have a 6.2p because this is a long thing to understand. So if one horizontal asymptote of this equation is 9 over 16, the vertical asymptote is negative 1/4, then what is a and what is b? Now this is a little hard. The vertical asymptote is negative 1/4, first of all. So this bottom function, we can actually, this is 6 by the way, not a b. We can actually use this bottom function to maybe try to figure out what negative 1/4 is. So 4bx plus 6 equals negative 1/4. 4bx plus 6 is equal to negative 1/4. So let's subtract 6. We have 4b is equal to negative 25 fourths. 4bx is equal to negative 25 fourths. So we have x is equal to so we have our second equation for our second problem. If one horizontal asymptote of this equation 9 over 16, vertical is negative 1/4, what is a and b? Now this is a pretty hard question. However, we know our vertical asymptote is negative 1/4. So we know that since our vertical asymptote is negative 1/4, we put x equals negative 1/4, 4b times negative 1/4, and then add it to the 6, we will get 0. It will be undefined since it's a vertical asymptote. So we will subtract 6. What's negative 1/4 times 4? Negative 1/4 times 4 is negative 1. So negative b is equal to negative 6. So b is equal to 6. So we got b, right? b equals 6. Now I said leading coefficients, you have to divide the leading coefficients to get a horizontal asymptote. So if one horizontal asymptote of this equation is 9 over 16, horizontal asymptote is equal to 9 over 16. So divide the leading coefficients. These are our leading coefficients. 3a over 4b is equal to 9 over 16. However, we already have our b. b is equal to 6. So we do 24. I'm going to do 24. 3a over 24 is equal to 9 over 16. So 48a is equal to 216, which leaves a as 4.5. 4.5, right? So a is equal to 4.5 and b is equal to 6, and that's the correct answer. So that's it for today's episode. If you want more courses, I'll probably start teaching history soon, as I've already released that video on history. I need to start making more of the Japanese lessons, and if you want to tell me whatever lesson suggestions you have, you can tell me, and that's it.